Okay, hello everyone and welcome back. Concordia University's For Space. Thanks for joining us again. This is another event. To help situate you again, we're streaming to YouTube live from For Space. We're located on unceded Indigenous lands in Montreal and Tiohtià:ke. For Space, we work with our university community to mobilize knowledge. We co-create daily activities, examining research, questions, and projects that are in development. We're running this event as a live stream meeting. Welcome any comments or questions. Anybody outside that'd like to come in and talk with Thomas, probably after, that would be great. I'm happy to pass over to Thomas from Space Concordia. It's Space Day here at For Space. Yes. Thomas will be speaking a little bit about some of the challenges, opportunities, and fun, I imagine, involved in software development, specifically for Space Concordia. And with that, we will pass it over to Thomas. Thank you so much for coming in.
Great. Can you hear me? Sorry? It works? So I'm good to go? Okay, perfect. So thank you for having me. My name's Thomas. I'm the command and data handling lead. Yeah, go for it. Thank you. No, go for it. All right, all good? All right. So let me share my screen. So we'll go have a look at my slides. So the presentation I prepared today is to kind of introduce everybody to what it means to develop software specifically for satellites, rockets, the different challenges that we have writing that code, because the conditions that we have in space are a lot different from what we can find here on Earth. So we'll go a bit over that. We have a lot of limitations when it comes to the hardware that we're able to use. So we'll talk a bit about that as well, and why we made the design decisions that we did in our project. So I'll give a quick introduction about Space Concordia. So Space Concordia is a student organization here at Concordia University. Personally, I'm part of the Spacecraft division, which was the original division in Space Concordia. Since then, we've had a few more divisions, such as the rocketry team, the robotics team, and the space health team. Spacecraft, we've participated in a few different projects since the organization was created. We participated in the Canadian Satellite Design Challenge, which we won numerous times. More recently, we participated in the Canadian CubeSat project, the CCP, which is a project which was funded by the Canadian Space Agency for 15 university teams to design, implement, and eventually launch their satellites. So we were luckily part of that. During that project, we created our project, SC Odin, which is now in orbit. We launched in June 2023, so this year, and we deployed from the ISS in July. And since then, we've been in orbit. And now, more recently, we just started our new project called CubeX. It's the CubeSats initiative in Canada for STEM, which is a project similar to the CCP, where university teams have to design, build, implement their 3U CubeSat for it to eventually get launched into space. So as I just mentioned, in 2023, so this year, we launched the first ever student-built CubeSat in Quebec. So that's the SC Odin. And to give you guys a quick idea of what the mission was, we were to capture images of Lake Kalu'e-Hapi. I'm not going to try it again. And the Namibian coastal regions to study aerosol particles present during dust storms. So that data was originally in collaboration with the University of Montreal, where we were to extract those AOD values and forward that to them so that they could update their climate models. We also have radiation sensors on board the CubeSat to evaluate the total ionizing dose experienced by the CubeSat during its time in orbit, because, as I quickly mentioned at the beginning, the conditions in space are a lot different from what we have on Earth. On Earth, we're protected from the radiation in space by our atmosphere. Now, since we're in low Earth orbit, we don't have that protection, so there's a lot more to measure there. And the main purpose of those missions, and the reason why the Canadian Space Agency started that project in the first place, is to train the next generation space engineers. So SC Freyr, that's the new project we just recently started working on. We entered the design phase officially in June 2023, and we're planned to launch in 2025. So that's part of the Cubics initiative, and it's consisting of two payloads. The first one is to capture RGB images of northern Quebec and Ontario in order to train a wildfire detection artificial intelligence model. And the second payload is in collaboration with another student organization here at Concordia. It's called AstroYeast. And we're essentially going to be sending different samples of yeast strains into space to study how they're able to survive and resist microgravity and the radiation. So, as I mentioned quickly, I'm part of the command and data handling team, which our primary job is to develop the software that's going to be controlling the CubeSat. So in order to do this, there's a few different things that we have to do. This is just a few of them. So we have to develop the drivers to interface with the hardware components, whether that be the reaction wheels that are on the CubeSat, the payloads that I mentioned earlier, as well as different things like sun sensors, thermistors, the heaters themselves, the solar panels, all of that. We have to prepare the data to be sent to the ground station. So we have to package them to different packets that it's able to transmit. Then we're able to reconstruct the data we were originally planning to send when all the packets are received on the ground station. We have to implement the different modes of operations and control the current state of the CubeSat. So as an example, if we're in communication mode, we have to make sure through our ADCS model that the CubeSat is properly oriented so that we're able to transmit data properly and at a fast enough speed. And then another important thing, which we'll cover a lot more later on in the presentation, is to test the software that we're going to be sending on the CubeSat. Because as we'll see later, once the satellite is into space, if something goes wrong, there's not much that you, well, in most cases, there's not really much that you can do to save your project. So we'll start off with the hardware because it's going to play a really relevant role in the rest of the presentation. So nowadays, most people are comfortable with this idea of computers, right? So you'll either have a laptop at home, a desktop. That processor is going to have 16 cores, maybe 32 threads, run at 3.9 gigahertz. For RAM, you'll maybe have 16 gigabytes of RAM, which in some cases you might even have 32 or 64 gigs. You'll have maybe 1 terabyte of SSD storage, sometimes even more than that. You'll have very fast speeds at almost 3 gigabit per second, and power consumption, 750 watts. That, from the research that I did, it seems like most power supplies are able to output that at the minimum. Now, we'll compare this hardware to the hardware that we use for, and the specs that we had for the SC Odin mission. So for our processor, we had 1 core, 1 thread, so a single processor running at a maximum speed of 300 megahertz. For RAM, we have 384 kilobytes, which is drastically less than what you can find in most modern computers. And for storage, about 2 megabytes of flash, sometimes less, sometimes a bit more. Very low transmission speeds, 115,200 bits per second, which is a fraction of what you can get on your computers nowadays. And maximum power consumption for the CubeSat at about 7.17 watts. Different modes of operation require less. Sometimes they'll pull 1 watt, 5 watts, etc. So now here's a little question for the audience. I want to know if anybody here is kind of able to figure it out. So we've all played with video game consoles before. Anyone want to take a guess at which console you can more closely compare the specs of SC Odin to? You already know the answer, so I'm not going to ask you. Would you like to try? PS5? Not quite. Which one? All Gear. Is that like a? Yeah. Is it like a PlayStation? Oh, okay, yeah, like the portable ones, yeah. Close, yes. So the one that I found that more closely resembles the specs for SC Odin is the Super Nintendo. So that's a console that came out originally in 1990. Similar specs, 1 core, 1 thread, total amount of RAM, 128 kilobytes with an extra 64 kilobytes for video RAM, so that's where you store all the data for your graphics. Storage, about from anywhere, depending on the game, right, because the storage is on the cartridge itself, 250 kilobytes to 600 kilobytes, that's kind of the average, and a power consumption of 7.5 watts. So overall, pretty similar to what we were working with SC Odin. So now that's the next question. Why are we using hardware with specs from about 30 years ago? There's a few different reasons. As I mentioned, there's a lot of radiation in space. And that radiation can have a big impact on the electronics that you run on your CubeSat or on your satellite in general. So whenever we're designing software for space or selecting hardware to run the software on space, we always keep that in mind. Because otherwise you can get single event offsets, so bit flips. So as you know, data on a computer is stored in binary format. So sometimes if you have radiation that hits your microcontroller, it can and has in the past modified like a 0 to a 1. And that can cause some issues later on in the software. Single event latch ups. Over time, the memory storage is going to degrade, so it's not going to do as good of a job at keeping your data. Your program's going to get corrupted, and kind of similar to that, the reliability of your hardware goes down with time. So in order to solve this, we try to use radiation tolerant components as much as possible. Now, in real companies, for larger CubeSats, you'll find radiation hardened components. Those ones are extremely expensive, way out of our budget, and the amount of stock that you can get is extremely limited. It's very much controlled. So for us, we have to settle for radiation tolerant components. Now, in order to shield against those issues, they have to manufacture it in a way that is a lot more expensive and lowers the maximum amount of efficiency, lowers the overall specifications that you can get for your component. The next thing that we have to keep in mind is power consumption. So a CubeSat is very limited in size. A 3U CubeSat like what we have, I'm assuming most people here have held a Rubik's Cube before. It's one Rubik's Cube and then another one stacked on top of each other. So the overall amount of space that you have for solar panels, for batteries is very limited. So you're not able to get as much power as you would on a larger satellite or by just connecting your computer to a wall socket. There's some components that have something called sleep mode, which allows you, when you're not using your microcontroller, to drastically reduce the amount of power consumption. So that helps you in the long term save your power for when you need it. And now, as I was saying, maximum output is 7.17 watts for the CubeSat at its peak. But most of that power is consumed by our payloads. So as an example, for the AstroYeast payload and for the AI model, especially the AI model, they're going to have much higher power consumption while it's in operation. So I have to pick components that don't consume too much, but are still able to complete what we need them to do. And then the last step is reliability, right? For our missions, let's say SC Odin, we worked on it for 4 years. If we chose some cheaper components and then we send them to space and then we get an issue with that chip and it stops working properly, it doesn't execute the proper instructions, and then we lose the mission. So then we just wasted a lot of money, we just wasted a lot of time to eventually get nothing. So when we're picking components, ideally we want to pick chips that have undergone certain types of testing, like radiation testing, thermal test, because the operating ranges for temperature in space are a lot wider than what you'll find here on Earth. And also, if we're able to use microchips that have been used in other space missions, that's even better, because then we have confirmation that this chip will operate the way we need it to. once it's in those conditions. Older components will usually have more community support. So that way, when we're looking for some information, when we're trying to implement something that we have never done before, we're able to find the information we need a lot more easily than if we pick the latest top of the line component, which doesn't have any of that documentation. It's a lot more work for us to figure that out by ourselves. And newer components may not perform as well as they're advertised. As I was saying, newer components lack all of that testing that I just mentioned earlier. So we can't confirm with 100% efficiency that they will operate the way that they are advertised to. So for the second part of this presentation, I'm planning on looking at some different case studies, 3 of them more specifically. So there are different space missions that have failed due to software errors. So we'll look at those and we'll see exactly what we can do in the future to prevent those mistakes from happening again and the lessons that we can learn from them. So the first project I want to talk about is the Ariane 5 rocket, specifically Flight 501, which is V88. It's, so a little bit of background on the rocket. Ariane 5 is an European launch vehicle. It's expendable, which means that once it's used, you can't reuse it again to launch future payloads like you could with the newer SpaceX rockets. And it's been used for many, many, many years to send payloads in space. It's known and is still known to be one of the most reliable launch vehicles that you can get. As an example, the James Webb Telescope is selected, like the people behind it selected that rocket to send the James Webb Telescope to space specifically because of its reliability. Throughout its entire lifespan, and all the flights that the rockets had, it's only ever suffered 1 complete failure, which we're going to talk about today, and 2 partial failures, which we're not going to mention. So Flight 501, its mission was to deploy 4 satellites as part of the European Space Agency's Cluster 2 mission. Those ones were designed to study the Earth's magnetosphere and the effects of solar wind on the Earth's environment. Now, as you can imagine, I said that mission was a failure. So when it launched on June 4th, 1996, the rocket experienced complete loss of guidance and attitude information 30 seconds after liftoff, which then caused the launchers to veer off flight and eventually self-destruct. Now, this was due to a design error in the software, and more specifically, an integer overflow error. So what happened? Before I move on to the next step, I'll just give a quick summary of how exactly is data stored in a computer. So as I mentioned earlier, like data is stored into bits, and we use bits to create bytes. So the data that I used a 16-bit signed integer in this example because that's the type of a conversion that caused the error. So here's the way it's organized. These are all the bits that are present in your for your variable. So the first one here, that's the signed part of a 16-bit integer. It represents if the number is positive or negative. And then the last 15 bits represent the number itself. So it's in binary form. So here at the right, you can see you have 2 to the power of 0. That is 1. So if this bit was set to 1, then you could add like a 1 to your number. So in this case, you would add 2 to the power of 12 plus 2 to the power of 9, and then so on and so forth, and that'll give you your decimal number. So here's an example. So this little bit string at the bottom here represents the decimal number minus 5014. This is just a random example that I wanted to show. So these are the steps, what occurred in order. So as part of their mission, they took a 64-bit variable and converted it to a 16-bit integer. Now, since your 64-bit has a lot more bits than your 16-bit integer, this the maximum number that you can represent with that is much larger than what you can store in a 16-bit side integer, which in this case would be 32,767. Now, since the value being converted was larger than that, the conversion failed and created an overflow error, which was never handled by the software, which caused the software to the main computer to switch control to the backup. Now, since the backup was running the same software, it entered the exact same issue, which then caused it to completely shut down. And then this caused the wrong value to be used in and then caused it to veer off course and self-destruct. And for anyone that's curious, I'm not going to try to understand exactly what's happening here because there's a lot of context missing, but this is the code specifically that caused the problem. Now, this code is written in a programming language called Ada, and this last line here at the bottom that I've highlighted caused the error. So just for anybody that might have been curious. So what happened from this? The European Space Agency lost a decade's worth of effort. They lost over $500 million and eventually decided to rebuild and relaunch their mission, which successfully launched in 2 phases 4 years later. The first two satellites, Samba and Salsa, launched on July 16, 2000, and Roomba and Tango launched on August 9, 2000. And from there, it was able to complete the rest of its mission. Next example, the Mars Global Surveyor. So this is a satellite which was designed to map the surface of Mars, capture data about its topography, its geology, its climate. It had a lot of different tools such as cameras, spectrometers, and different instruments to be able to achieve that. It was also, one of its main missions also was to find evidence of water on the surface of Mars or beneath it. So the mission was originally meant to last about 687 Earth days, which is equivalent to 1 Martian year. But the project itself went well and actually went way past that original estimate and operated for a whole 9 years. Now, what happened to this project? I said I was going to show examples of projects that failed or that died due to software errors, which is exactly how this satellite went out of commission. So in June 2006, there was a software update that was uploaded to the spacecraft, which caused a memory load command to be sent to the incorrect memory address and overrode and corrupted some positioning parameters. Now, this didn't cause any issues for a few months because there wasn't any command sent to reposition the solar panels. But when that command was sent on November 2nd, the solar panels were moved a lot further than they should have been able to, which like a failsafe detected this, concluded that the panel itself was jammed and caused the satellite to go into safe mode. Now, since it went into safe mode in a position where its battery was exposed, it wasn't able to reposition itself properly to prevent this problem, what happened. But in the position that it was, one of its 2 batteries was exposed directly to the sun, and which caused it to overheat and then eventually kill the satellite. Now, it's unknown if that satellite how much longer that satellite would have run for, considering that it was already way over its original estimates. But it's still an issue that could have been prevented with better testing and implementation and design of the software. So yeah, it was, as I was saying, the mission still lasted a lot longer than was originally designed to. The mission, however, was still a success. They were able to find evidence of water, and that data was eventually used to select a future landing site for a Mars rover. Now, following the death of that satellite, there was an internal review board that determined that the existing procedures that they had in place to detect those errors weren't sufficient enough, and then they recommended some changes and more thorough reviews of all changes to stored data before they were uploaded to the spacecraft. So these were the lessons learned from that. And then the last example that I have here to show is the Mars Climate Orbiter. So this satellite was part of the same type of mission as the previous one. It was originally meant to be the Mars Global Surveyor, the Mars Climate Orbiter, and then a Mars rover to be sent all approximately at the same time. So the Climate Orbiter was meant to be sent in orbit of Mars, and then for the first 3 months of operation serve as like a communication relay for the Mars rover. And after that, it would conclude a 2-year mission to monitor atmospheric dust and water vapor. Unfortunately, though, that didn't go to plan. As the satellite began its approach into orbit, nothing was ever heard back from it. There was no contact ever established with that satellite. No signals were ever received. So it was concluded that the satellite missed its orbit and disintegrated in the Martian atmosphere. Now, the error is relatively silly one. The data that the satellite was expecting was in English units. The data was sent in English units, so more specifically pounds per second, but it was never converted to the metric standard before being uploaded to the satellite, which would have been in newtons per second, which resulted in it interpreting the data completely wrong, missing its orbiting period completely, and crashed directly into the atmosphere. That was the wrong slide. Just double check. Yeah. Okay. So, what kind of measures can we take to improve our software, to make it more reliable, to make it, because that was kind of the point of the presentation, right? To look at a few different examples and see how exactly our methods have evolved over time to produce more reliable software. So the first section I'm going to talk about is the Power of 10. It's a set of 10 rules created by Jared J. Oltzman from the NASA/GPL Laboratory for Reliable Software. Now, the main purpose of these rules were to eliminate some more dangerous C coding practices, which would either make the software more difficult to review, to statically analyze, or just in general, like more dangerous coding practices. These rules are meant to be used alongside coding guidelines such as MISRC or AUTOSAR, which I'll mention after this section. So it's composed of a few different rules. As I said, 10 in total. So the first one that we're going to have a look at is to restrict our code to more simple control flow constructs. So as an example, recursion can make your code a lot more difficult to understand, to statically analyze. It can break the functionality of some softwares that are meant to analyze your code and make it more difficult to review, troubleshoot different conditions, if something goes wrong, to debug it. We also want to avoid using statements such as go-tos, set jumps, long jumps, etc. Because we want to make sure that the control flow is as simple as possible. There's always better ways or more efficient ways to implement what we would do with either recursion or go-tos. So we want to stay away from that as much as possible. Now, the second rule is when we're implementing a loop, let's say in a case that we don't have a choice but to use recursion, or we're using a for loop, a while loop, a do while, any type of loop, we want to make sure that we have a fixed upper bound. So what that means is that for any loops or any recursion in the project, you can only iterate a certain maximum of times. So as an example, that depends on your need. That could be 1,000. So if your condition is not met in your loop after, let's say, 1,000 iterations, you just break out of it and resume the flow to the next steps. So this is to prevent runaway code, infinite loops, all of that. Third rule, no dynamic heap allocations after initialization. So if you have a good understanding of C, that means not using things such as malloc, free. If you're more comfortable with C++, that means avoiding the use of the new or delete statements, which is kind of the equivalent of malloc and free. Just this rule alone eliminates a whole lot of issues that are caused by improper heap usage, such as memory leaks. Now, in the with a memory leak on a project where the memory is as limited as what we have, that can get out of control very quick, especially in a project where that code will run for 24 hours a day, 7 days a week for months, even sometimes years. So these kind of guidelines regarding heap allocations are already present in most coding guidelines, such as MISRA-C, AutoSAR, or any other alternative that you might be able to find. It's a very common thing to want to avoid when you're developing embedded software. Because as an example, let's say you're writing an application for your computer. If you have a memory leak, what's the worst that can happen? Your application will crash after a bit. You'll have to restart it. It might get a little bit slow, but still be usable. All pretty, not really impactful consequences. Meanwhile, if your software on your satellite fails because it gets a memory leak, it's not able to perform the proper execution, the proper instructions, then you risk losing your entire mission with all the work that you did if you're not able to recover from that. Fourth rule, no function should be longer than one printed page, which is approximately 60 lines of code. There's a few reasons why we want to do this. First of all, it makes the code a lot more readable. It makes it possible to test every single function as its own unit, compared to having one large function that does many things. If you want to test a specific section of that, it becomes a lot more tricky. Functions, and also in general rule, functions should only perform one single task, the task that they're supposed to do. So if you're trying to calculate, let's say, what could be a good example? Let's say you're collecting data from the thermistors, and then you're converting that, like the analog signal, to data that can represent a temperature. Now, you would create a function that, first of all, is going to get that data from the thermistors, which is then going to, the next line will then use that data that you just collected to convert that signal to a temperature, and then you can do whatever you want with it. If you put all of that functionality in a single function, when it comes time to test getting data from those thermistors individually, then, or if you just want to test the conversion without getting the data from that hardware, you don't really have a choice but to do both at the same time. So that's kind of one of the reasons why you want to avoid longer functions. And usually, most of the time, when your function is very long, it's typically a sign that your software isn't structured very well, and that you're following some pretty poor coding guidelines. So that's definitely something that you want to avoid. Let me just get a bit more water. So rule number 5, every code function should have a minimum of 2 runtime assertions, or at least an average, right? Because in some cases, you're not really going to be able to test for different things all the time. That can be different preconditions, that can be different post conditions for your project. It could be the parameters of a function, the return values. Most of the time, the statistics show that every 10 to 100 lines of code on average, you'll have at least one issue, one bug. So by using those assertions, you're able to confirm that the data that you have is what you're expecting, if it falls between certain bounds, if it's the type that you expected, if the data even is there. So these assertions, where you're adding them to your function, should not have any side effects on the rest of your code, which means that if in the future you decide that performance is very critical for that function and you don't want to be running those assertions all the time, you can just delete them without the risk of damaging the rest of your code. Rule number 6, declare variables at the smallest scope possible. That's essentially applying a basic principle of data hiding. Let's say that because let's say you're writing some code, you initialize and you define all of your variables at the beginning and the top of your function, and then your code gets very, very long. Well, you run the risk of accidentally modifying a variable that you don't mean to modify. And then if you notice that this happens, then you have a lot more code that you have to go through to figure out where exactly that happened. So by keeping your variables and your data at the smallest scope possible, it makes it a lot easier to, first of all, avoid the risk of accidentally modifying that value. It makes it a lot easier to debug and troubleshoot where exactly that mistake was made, because you have a much smaller section of code to evaluate. So also, it's not always going to be the person who wrote the code that is going to debug it. So by using those principles, it makes it a lot easier for whoever else is there, because they won't have to try to understand an entire files, like an entire massive section of your code, just a little bit, a little section. Rule number 7 of the power of 10, we're getting towards the end here. Return values should always be checked for every function. That includes functions that you don't really need to get the return value. A good example of that, well, at least a simple example of that most people can understand, is the printf function. Now, you don't need any return code from that, because if it didn't succeed, if something went wrong, you just didn't print anything to the console, right? It's not the end of the world. It doesn't impact your code that much. Might be annoying in some cases, but it's not really a big deal. So you want to disregard the return value for that. So what you want to do is you want to cast that function to void. Now, it doesn't really change anything in terms of your code. This is purely for visibility, because when you start reviewing your code after, when you have other people that are going to review your code after, if you have a function there that's called and the return value is never like checked to make sure that the code went properly, if you haven't identified that you're ignoring that return variable, they might start investigating why it wasn't done. Why is it irrelevant? So you want to make sure you document that as much as possible. So either you can cast it to void like that, which is a good way to do it, because that shows that you actually meant to disregard the value, or you can just add a comment explaining your decision, because in some cases it's not always clear why the return value was ignored. So having a good comment there to explain why exactly you're disregarding that value is always a good thing to add. Rule 8 is limiting the use of the preprocessor in C. Now, it's a very powerful obfuscation tool, but it has a massive impact when you're starting to use text-based checkers or external tools that will analyze your code, because it makes it a lot more difficult for them to understand exactly what you're trying to do with this. So usually when you're using the preprocessor, you want to limit yourself to using only including header files and very, very, very simple macros. Also, one of the other impacts that using the preprocessor will have is that it will create many different versions of your code, which, let's say, if you have 10 different values for what your preprocessor macro could be, you have to test all your software 10 times with each different parameters. And if you have a lot of them, then it starts becoming a lot of different versions to test. So definitely something to avoid if you're using C and C++. Rule 9, we want to avoid the use of pointers because whenever you're directly interfacing with memory in that way, it can cause a lot of confusion, especially if you're not using the heap. Sometimes you create a pointer to a variable that's already been deallocated, so you're pointing to bad data, to nothing, and that can cause some runtime issues down the line. If there is the need to use pointers, usually you want to stick to a single level of dereferencing at a time. So if you have, let's say, a two-dimensional array that you're storing using a pointer, so let's say char and star star, you want to dereference the first array separately, and then from that variable you just created, dereference it a second time. You want to try to avoid dereferencing it twice in the same statement to make your code more readable and easier to understand. Another very dangerous thing with pointers is function pointers. Now they should be used, well, at least they should not be used unless you have very strong justification. And the reason for that is once you start using them, it's impossible for your tools to test for many things. One of those being like the absence of recursion, like sometimes, which makes debugging a lot more difficult. And then the last step is kind of like the more intuitive one. Whenever you're writing software, you want to compile with all of the warnings enabled and try to approach all of those warnings, fix the issues so that it's gone. When you're compiling your code at the end, you shouldn't have a single warning or error left over. Now, the reason for that is we have very efficient static code analyzers out there. Even in your IDEs, the ones that it ships with are very powerful. And there's even some very good open source implementations out there that are free that can be used separately. Because sometimes those warnings might not seem like they're a big deal, like you feel like you can ignore it. But sometimes those warnings might cause some issues down the line as your software gets more complex, has some functionality that you didn't originally mean. So if you can avoid all of those warnings at the maximum level of strictness, then you're making it a lot less likely for such mistakes to happen later on in the future. As part of this step, which is going to be my lead-in for the next section, is you want to try to use static analyzers whenever possible. So these static analyzers, which we'll have a look here, are tools that you can use to analyze your source code directly. So what that means is that unlike when you're debugging using your breakpoints, your step into, your step out, you don't need to run the code for those tools to be able to work. What they will do is they will examine every source code file in your project, try to find some patterns that are a bit more dangerous, tell you maybe you should fix them, modify them a little bit to avoid potential issues such as memory leaks, off by one errors, etc., etc. So they're used more commonly in the early stages of software development when you're working on smaller sections of your code independently from each other. You can't really run everything as one big unit yet. So it allows you to identify some possible issues that you might encounter in the future, some defects in your code. Maybe you wrote something, but it's not going to behave the way that you expected it to. It can give you some warnings regarding that, and also some potential vulnerabilities. So these tools allow us to enforce some coding standards, such as MISRA-C, AutoSAR, which are composed of like hundreds of rules, which would be very difficult for a developer to manually figure out all the different instances of a rule being broken, a guideline not being followed. This will automate all of it, report it to you so you can attack that specifically and modify it to resolve that potential issue. Now, these tools will help you write your code to be a lot more readable, a lot more maintainable, and it's important also to understand that using static code analysis doesn't replace the need to test your software dynamically. So by running the executable either in an emulator or on actual hardware and running it through a lot of different case scenarios to see if it behaves the way that you're expecting it to. So this is just an extra step that you can add on top of your development workflow to try to reduce those errors as much as possible. So looking back at the first example we looked at, the Ariane 5 rocket, where there was an overflow error, using static analysis software, at least the modern ones that we have now, would most likely have helped kind of detect this vulnerability. So talking about coding guidelines, one very popular guideline used in critical systems is called MISRA-C. They're a set of guidelines that was originally designed for the automotive industry, but have found application in a bunch of different safety critical systems, such as automotive, industrial, aerospace. So all devices that you can't afford them failing. So these, in some of these industries, following and being compliant with these guidelines is often a contractual requirement. So it's something that you'll have to enforce no matter what. So it's definitely a good thing to get familiar with. So there's these coding guidelines are separated in two sections. You'll have your rules, which are mandatory and you cannot break. If you are found to be in violation of those rules, you have to modify your code to be in a way that it is compliant. And there's also guidelines, which are more recommendations, things that you should try to do, but it's not really mandatory, but it would still be a good idea to follow to avoid future issues in development as your project scales up. So here's some example rules from MISRA-C. All declarations should be at block scope, so you want to try to avoid global variables as much as possible. You shouldn't have any. All automatic variables should have been assigned a value before they are used. So that way, if you have an automatic variable, you already know kind of what type it's going to be. The increment and decrement operators should not be used with different operators in the same expression, the same line. So let's say you are navigating through an array, you want to move to the next step. Instead of accessing your array and then putting your index and then putting plus plus into it, which will work, you want to try to avoid that and separate that increment or that decrement and putting it on the line after, which will help make your code more readable. And then here's an example of a guideline. External identifiers should be unique to avoid conflicts when you start importing different libraries or different sections of your code. Now, there's also AutoSAR, which I mentioned, which is an evolved version of MISRA C++. So it's basically similar guidelines, similar rules, but they have some sections that are designed for C++. So think polymorphism, object-oriented programming, templates, all of that C++ functionality. There's a lot more rules in AutoSAR to cover that. So I talked about static analysis, now let's go over dynamic analysis. What that is runtime analysis. So as I mentioned previously, that's when you have an executable of your code that is working, you're able to either run it on the emulator, run it on the hardware, and then you're able to start analyzing what the behavior of your code is. So you can use different techniques such as profiling to figure out, to collect data on the execution of your program. So that could be CPU usage, memory usage, all stuff like that. So as an example, this could help you detect potential memory leaks. If you have a function that has very high, or a section of your code that has very high CPU usage, maybe you can find a way to decrease that. Unit testing, which is another very important part of software development, is to write different test cases for every kind of section of your code. So earlier in one of the rules, we said that code should be, a function should only have a single objective. It should only be what it's designed to, doing what it's designed to do. So that way you can test them all as units, which is exactly what you're doing here. You're coming up with test cases for that function. So as an example, if you want to if you want to test the reaction wheel and you want to enable it with different values, you can either toggle it off, with, let's say, a variable of 0, or you can set the speed, let's say 5, test it with that variable, and then you can see if it's behaving the way that you're expecting it to. So the more test cases that you have, the better, because you can show that your code is reliable and behaving the way that you're expecting it to. And sometimes you'll find some bugs that you didn't even imagine, did you even think would happen, some behavior that's completely different than what you anticipated. So using those test cases will allow you to find those issues. You can also use the debugger, like what we talked about earlier, when you're adding breakpoints, when you're using step in, step out, when you're looking at variable allocations, what's in your scope. So debugging, most of the time, when you're starting to write code, that's your first introduction to dynamic analysis. It's a very powerful tool to try to figure out what went wrong in your code, why it's not working the way you anticipated it to, because you can relook line by line, see how that line of code is affecting your overall process, and see what you can do to modify it. And then logging and tracing, so basically just recording the behavior of your program, either like, let's say, logging to a console, writing it to a file, so that you can review it either at the same time or later on. As an example, with our CubeSat, we have a log file, and whenever we're doing some operations, we write them to that file. So we're able to retrieve that data later and then examine if it's not behaving the way that we anticipated. We can kind of try to understand what went wrong and in what order things happened. And here's the last step, which most people are not familiar with. It's a process called formal verification. Now, this is something that we are starting to use in Space Concordia as for this project. This entire process is the reason why we switched away from using C++ to using the Spark Ada programming languages, because that language supports formal verification. Now, what is formal verification? If you've ever done discrete mathematics, you probably have some experience with proofs. So your direct proofs, proof by induction, proof by cases, contradiction, contraposition, all of that. We're applying a similar process to our software. So we're using a basis called contract-based programming, where functions will have preconditions that need to be fulfilled and post-conditions that specify kind of the way it's supposed to behave. I'll have, after this slide, I have a little code example that kind of shows using Ada Spark how you can write some code to with these preconditions and postconditions. Now, these formal verification systems use programs called provers. Now, these provers, what they're going to do, they're going to use formal methods such as mathematical proof techniques to verify that the program that you wrote, the function that you wrote, adheres to your contract, and that no possible value will that all the possible values will be will involve the code running properly. So what that means is that using these provers, I can prove that my code will 100% of the time never have any runtime exceptions, which when we're writing software for critical systems like this, it's an extremely interesting advantage to have, because once we've implemented some functionality, we can just prove that it functions and then never have to come back to it again unless we need to add some functionality on top of that. So that makes our code that much more reliable. For formal verification, it's a very iterative process. So, as I mentioned here, if a proof obligation can't be proven to be true, the prover will be able to give you some counter examples to demonstrate why your contract failed. And then from the data that you recovered, you're able to modify your contract to keep those test cases in mind. So sometimes that'll be modifying the implementation of your software. Sometimes that'll mean modifying your contract itself. Or sometimes it'll show you there's some conditions that you didn't think about that could happen. So what can you do? You can modify maybe your precondition to only allow certain types of variables to be used. As an example, let's say that your code doesn't work with negative numbers, but it's not supposed to. It's only supposed to work with positive numbers. You can set a precondition that will restrict one of your parameters, whatever you're giving to your function, to be a variable greater or equal to 0. So that way you just removed all of the need to test for negative numbers, because first of all, it's not something that you need in your implementation, and it doesn't make sense in your case, right? So here's a small example of a Spark Ada program. So this is an implementation of a binary search algorithm using Ada Spark. So at the top here, you have what would be in an ADS file. If you've used C and C++, that would be the equivalent of a header file. So you have kind of the description of what functions are going to be implemented, if there's any variables, what's part of your package. So here, as part of my binary search package, I enable Spark mode, and I have a function called binary search, which will take in an array and a value. It returns a Boolean, and then here's the conditions that I have for it. The precondition is that the array has to be sorted. That whenever you're working with binary search, if you're familiar with the algorithm, it only works if your data is already sorted. So here I can confirm that. Then I can check that the last value in my array is less than the maximum number, the maximum positive number, which basically just means that if I can avoid like, let's see, just make sure that the data is in the right kind of bound, in the right range. So I can confirm and I can prove using this contract, this specification. And then for my post condition, I just want to make sure that the data I've recovered from that binary search function is actually part of my array. So here I'll just check binary search, the result from that function has the value has the value VAL, and that is part of the A array. If you can come up with a different post condition that has to be true every single time, you can just use kind of similarly to what we did here in the precondition, the AND statement. And then, so you do this and then whatever other condition you want to test for. And then the implementation of your code, it doesn't really change really. It's mostly just the contract at the top here that has to be defined. So here you have the implementation of the binary search algorithm. So with the provers, I can confirm that this binary search algorithm will never fail. It will never have any runtime errors. So I can safely use it throughout the rest of my program, and I'll never get some issues from that piece of code. So as I said, it's an iterative process. So maybe the initial conditions, the preconditions, post conditions that you'll give it will be wrong, but you can always modify them so that it fits your need, and so that the prover is able to do its job and prove that you'll never run into any runtime exceptions. So conclusion, that's basically it. The idea of the presentation was kind of to initiate people to the different steps. Now writing code for high reliability, whether it be medical, automotive, space, all of these uses, most of the time you'll have a massive amount of money on the line, a lot of work, or sometimes it's going to be human lives. As an example, in the medical industry, there's been some cases of people dying because software wasn't properly written, some bugs in medical machines, like irradiating people, causing them to die. In the automotive industry, especially as we're moving forward with like more automated vehicles that have different tests, like different sensors to help you drive, keep you safer. If you write software that'll not establish the use that you're expecting it to have, well, you risk you have the risk of somebody having a collision and maybe becoming handicapped or even dying. Kind of same thing for space, right? The space industry is growing very fast, especially now that the ISS is going to be retired in the next few years. The public sector will start creating its own space stations to do some research. Space tourism industry is booming. So there's a lot more applications where human lives will be on the line, where different projects will surface, will be launched. So the importance of writing software that's safe, reliable, and has never really been more necessary than it is now. So these skills are extremely necessary. And if for anybody that's interested in going to any of the industries that I listed, it's definitely something that you want to start getting familiar with. So for me, I'm done. So if there's any questions, we can kind of do like a Q&A, maybe go back over a section that I might have missed, or if you have any questions about anything that I've said. Thank you. Good, perfect. So thank you, everybody, for having me. It's been a pleasure. Ford Space is a very beautiful environment, and for anybody that might have watched this online, we're here for the next hour. If you're nearby and you want to stop by, we're still doing recruitment outside. If you want to ask some questions about Space Concordia, you can feel free to stop by.
Thomas, thank you so much. We're going to end the live stream now, but it'll be available on our YouTube channel if you ever want to check it out afterwards. And yes, thanks again, and thanks for everyone for coming in for Space Day. Thank you.